Okay, everyone. So this is really the last lecture about chapter 3. I'm going to finish that parabola problem, probably actually start it from scratch and make a few comments. I'll just take it easy for this lecture, and then we'll move in next door and we'll start systems of particles, kinetics of a system of particles. Now, do you have any questions, any concerns? Is there anything that is really making you struggle a lot at this point in kinematics? In kinetics, in any of the problems?
The relative velocity concept.
The relative velocity concept, okay.
The whole reference frame thing, I still need to practice it.
Okay, so we're talking about this definition. We said if we're given a generic reference frame, this is important stuff, and it's important for your test too. So given a generic reference frame A, with a certain origin O fixed in A, we said we assume we have a generic rigid surface S and a point mass P moving on the surface. We called a relative velocity between the point mass P and the surface the following difference of vectors V of the point mass M in A minus the velocity of the point of contact as seen belonging to S. So we actually look at P, which in this particular instant of contact between the mass and the surface is part of the surface. So the next time step, if you think about in terms of time steps, the mass will be here. P was the guy where the mass was in contact before. Then it's the new point here. But you look at it as part of the surface as seen by an observer in A. And we demonstrated that this is independent from the reference frame, right? So this was the definition. So every time you have a problem, you apply this definition. You really want to go back to the basics for every problem you need to solve. But in many cases, like the example of the ring and the color on the ring, we said, okay, in this case, the surface S is collapsing to this line in 3D Euclidean space. And since I am giving you the freedom of picking A as you prefer, notice that here there is no reference frame, so the VREL is really independent of the reference frame you choose. We said in this case, we pick A to be equal to S. And you can do that every time. Actually, most of the problems, you probably will do that, because it's easier for you to find the relative velocity, because if you make this assumption, the VREL is only going to be the velocity of the point mass here as seen by S. That's it. The second term goes to 0. Are we all following this? We've done it a couple of times in problems, actually. So I'm not saying that this is what you will have to do every single time, but because that is the starting definition. So this is not the final solution or recipe that I'm giving you to compute the relative velocity for every problem. That is the definition. That is the one you want to start from. But then in many cases, you may look at the problem and say, okay, I know how to compute the velocity of this mass if I imagine that I'm sitting here on the ring. Whatever the ring is doing, moving in space, rotating, I don't care. I can easily compute the velocity of this point here of mass M as seen by this reference frame, which is S.
So that means the velocity of point P as...
No, this is the velocity of point P is
S as seen by A.
It's
the notation of that.
Say it again, what is the question?
The second term.
The second term.
The velocity of point P and S as seen by A.
As seen by S.
Okay.
Because again, I am free to pick A to be any reference frame.
Okay. So when you make A and
I
S equal, you get that to be zero.
Right, I assume A to be S. So instead of being basically out here and looking at things from another reference frame A, I'm actually right here on S. And I can do that. It's perfectly legit. That is completely reference frame independent. So that brings this second term down to 0. And it makes me focus only on the motion that is seen by an observer fixed in the surface on which the particle is moving. You may actually end up doing this every single time, because what happens in problems is that you do pick usually your surface S as one of the reference frames for the problems. So it is already there for you. You've probably built a coordinate system which is fixed in that frame, which we did for this problem. And so you can easily or quickly compute these without worrying about this point here. But a good exercise is going back to, for example, this problem, and don't pick S as your A reference frame. Use the ground and apply that definition, and you will get the same result, of course. You must get the same result. Otherwise, there's something wrong with the definition, which we demonstrated is independent from the reference frame you pick. So in that problem, I chose to pick S because it made my life easier. Pick G, and you should get the same relative velocity, which we said that this, in this case, was something looking like V rel was, I don't remember the problem, was some R theta dot E theta or something like that, right? Which makes sense. If you think about it, that point is constrained to move on the circle. If I am sitting on the circle, all I see is this point moving tangentially along the circle, right? That's why it's called relative velocity. It really focuses on what happens between the surface on which you're moving and your particle. It doesn't matter if you take this surface and you throw it in the air. What matters is how the particle is moving on that surface to give you the friction force. That's really the end goal for what we were doing last time or a couple of times ago.
So you can say that in layman terminology, that'll be, you're seeing the velocity of the actual particle, seen in some reference frame, minus the velocity of the reference frame where the particle is sitting,
Yeah.
as seen in that same reference frame.
Yeah.
Okay.
Yeah, this is the definition. That is the definition. The definition of relative velocity is the difference between the velocity of the particle as seen by any reference frame and the velocity of the point of contact. And the point of contact is defined as a point that belongs to the surface on which you're moving as seen by the same reference frame. So again, imagine something moving on this table, and then I start moving the table around. All you care is what happens between the table and that particle. And that definition is actually giving you that. And again, this may be the solution that you end up using all the time, but it may not be. In some problems, I don't know, I'll make up an example maybe, but in some problems you may have already solved for these two, for another reason, right? So if you have them already, just subtract them. If you don't, then maybe you're better off picking A as S. But this is the starting definition, the most general one. Make sense? Do you have any other questions on this? This is a good time to ask questions. No? Okay. Any other topics that are of concern? No? I'm going to continue on that problem with the parabola, yes. I want to spend a little more time on that before we completely switch gears and we move to a new chapter, which is next lecture, or at the end of this one, depends. Now, I am assuming that everything I've done so far, especially in terms of examples, you guys have gone back home and you've tried to solve them by yourself, either finish them or much better, start them from scratch and try to solve them by yourself. That's what is expected from you. So you probably have tried to finish this, but let's give it a little more thought here because there's a lot of nice simple principles that we have defined that we can apply here. So we said we had a parabola given in the following form, x squared over 2b, right? There is gravity here. I'll call this EX. Call this EY, I believe. And of course, easy sticking out of the page. So you have your point P of mass m, which is moving without friction on this parabola. Okay. And I wanted to find the equations of motion using the two forms of the work energy theorem. Remember, we defined two different types of energies. Kinetic energy, T of a mass m, of a point mass m, is 1 over 2 m v in n, dotted with v in n, where n is an inertial reference frame. Okay, that was the definition. We also defined conservative forces and said, okay, if a force is conservative, it means that I can express it as the minus the gradient of a scalar function, which I call the potential function, which is a function of the position of my particle, right? We just gave these definitions, and we derived pretty easily that the rate of change of the kinetic energy in the inertial frame n, remember this is a scalar, so I can do this without specifying anything here, is equal to F dotted with Vn, where F is the resultant of all forces acting on the particle. If the forces are divided into a component which are non-conservative and another component which is conservative, you can find the alternative form of the work energy principle, which is d dt of T plus U equals the same dot product, but now it's only applied to the non-conservative forces. And we noticed, okay, this can be 0 if all forces are conservative, or they are always perpendicular to the velocity as seen by an observer fixed to the inertial reference frame. Okay, and so I wanted to solve the problem. We didn't really do much, but I wanted to solve the problem with the two different forms here. And I think that's a nice exercise to do. There is some algebra involved. Of course, you should get the same result. They are just two alternative forms of the same thing. They're not laws, they are derived results. They should give me the same final equation. And we commented the last time that this is one equation. This is one equation. It's either one or the other. It's the same one. So you have only one equation of motion in this case, which makes sense because my problem is parameterized by the variable x, right? Y is a function of x. So if I give you x, you know where the particle is. We all remember this? We all agree with this? And I think where we left off last time, actually, so I can probably erase this. We were discussing about intrinsic coordinates, actually, right? And so we said if I'm looking at that, I zoom in that portion of the parabola, and this is my point P, I know that I have the gravity, the force of gravity here, and the reaction from the parabola itself, which is a rigid surface. I said that the parabola was fixed to the ground, which is an inertial reference frame. And we said, okay, if this is fixed in an inertial reference frame, the parabola is fixed, then the only reaction component that I should be worried about is basically perpendicular to the tangent direction here. I don't care about the binormal direction. I mean, you can, in principle, you can write that there is a reaction, but if I know that there is no motion happening on the z-axis, that reaction doesn't really matter. It's not going to affect us. It's not going to give us a differential equation of motion. It's always 0. Z dot and z double dot will be constantly 0. So who cares about that one? But but say that actually I am in a case where I have to care about it. So what do you do? Well, then we said the friction force is along the tangent. Okay, fine. And actually, if there was a friction, in this case there isn't. You have to do something like this if it's Coulomb friction. So you have to compute VREL. So that should not be a concern. Now the actual reaction here in the general case will be Rn we said plus Rb EB. So if you were in a case where the parabola is spinning and you really need to care about both of them, well, you must write this too, right? Nothing you can do about it. How do you build these two? Intrinsic coordinates, go back to your notes. You may see a problem where you actually have to define those vectors because
So
En is
in the inertial reference frame divided by its magnitude.
so we start from ET, right? That's what we done last time. It's V, well in this case it's V in G, right?
Yeah.
Over its norm, which we will compute and write. Then we said En is d et dt in G, in this case, over its norm. Correct? And then what is B? Et crossed with En? Is that how we done it last time? No? Yes? Maybe? Now, my question for you is, so this is one of the problems of your test. Do you, and you do have to, unfortunately, care for the binormal component, so you have to go through this painful stuff. Do you really have to go through the whole thing? What would you do? I mean, you still have to tell me what En and B are, but is there a way to do it that doesn't force me to do every single step here? What do we know about these intrinsic coordinates? We quickly described this. We said if we have, a curve in 3D Euclidean space, you focus on a certain point here, and you're moving on this trajectory at a certain velocity v in A. Okay, the unit vector along v is what we define as ET, and that's fine. But then we said there is an imaginary circle here, the osculating circle, that is touching the curve at that point. And we observed, and you can go back to your book and read more about this. We said, okay, the normal, which we define that way, is going to point at that all the time, right? Okay. So in this case, I don't really have to probably do all that. Maybe. In this case, I expect at least the normal to be this way. Correct? That doesn't tell me how to express it in this other coordinate system yet. But, I make that observation. Now, which way is the velocity now? ET. Which way is ET, though? Yeah, but tangential is not enough, right? It doesn't give me a direction. So basically, if you... How do you know if it's up? This is a discussion here. There's no secret or answer that I'm expecting from you. There is no specific answer that I'm expecting from you. But how do you know if it's up or down? How would you know?
Just choose direction, it turns out. Does it depend on which way it's spinning?
It's not spinning. Say that it's not spinning for now. For now, so I went away from writing the equations of motion for a second. I'm just worried about figuring out these intrinsic coordinates just for fun, for this problem. So it's not spinning. Probably it's not spinning. And even if it was...
Yeah, if it isn't spinning, then...
Yeah, if it's not spinning.
Yeah.
Yeah, you're right. If it's spinning, that affects the velocity. That affects the velocity seen by the inertial reference frame, right? But you can still put yourself in the reference frame of the parabola and still work with these vectors. That it's actually what I'm doing here. So say that I'm sitting with the parabola. I am in the reference frame of the parabola, so I really want to define the vectors that way. Because that's what we've done. When we defined the intrinsic coordinate, I said I have an external reference frame, and I look at the trajectory from that reference frame, and I define ET parallel to the velocity seen by that reference frame, and then the other two come with the definition. So that reference frame can be the parabola itself. So let's say that I'm focusing on that because that's what I want to do. I decide that I want to use an intrinsic coordinate that is defined as being attached to the parabola so that I can write r still that way. So if it rotates or not, I'm still sitting with the parabola and I see the velocity from the parabola's point of view is tangent to the parabola, right? So that still doesn't solve the problem of saying, is this going this way, ET going this way, or is it going this way?
But why you need the direction? Because any
Well, EB would be
In or out.
in or out. It doesn't, I mean,
That would depend on the direction of the velocity itself.
right. So, and what gives you that? What will give you that? So when we get to finding the differential equation of motion, we stop there, right? Because this is not a class on numerical integration or solving differential equations. But if you get a differential equation and you need to solve it, what do you need?
Initial condition.
Right, you need initial conditions. So if this thing was starting, say, this point was starting here at rest, there is gravity, I definitely expect it to go down. So I probably can say that the ET is going to point that way. But if this object is actually starting, I don't know, down here with a pretty high velocity, and it can actually be going up at that point, then eventually will go down. So that really depends on the initial conditions, right? So it's hard to tell. That's my point. It's hard to tell in this case. You really have to know which way you're moving at that point, which you don't. So how do we do it? We can still do it. What is the velocity g? We can find it. I'm just thinking out loud here. That if I try to actually guess it, I can guess En, and that's okay. I know it's perpendicular to the tangent direction. That is going to work. But ET can probably guess it. And so EB is going to be in or out, right?
So velocity in the last class, you derived it as x dot in the EX direction plus x times x dot over b in the EY direction.
Right? Oh, I'm sorry. This is the velocity, right? So ET is this same vector over its magnitude, right? Make sense? Okay. What do you want to do next? Well, you can simplify stuff, but can we simplify this?
And you can factor out x dot over b.
Over B, I don't know if I want to do that.
No, yeah, just an x dot.
Okay. That's my ET. What's next? Of course, I can take the rate of change of these. I can do it. I can apply En being equal to d et dt in G t in G. And I probably will have to do that. I'm not saying that I'm trying to find a shortcut. I am just
I'm just thinking that given that equation,
right.
suggests that the ET vector velocity when x is positive and negative when x is negative. Because of the denominator, you just have positive numbers.
Okay.
The only thing that would.
Right. Yeah, no. That's thinking. We're thinking here. I don't have the final answer. I mean, I do have something on my papers, but I don't care. I'm doing it with you. I'm not just doing it by myself. So, okay. So his point is that this is a unit vector, right? And say that you are in this quadrant here, and x is positive. The first component on ex is positive, right? And then second one is positive. Okay. So that is probably the this solution here, right? Looks like. Does it work if I am on the other quadrant here? Well, I guess it's pointing this way. In this case here. So for the type of setup that I have, with this coordinate system that I picked with x positive going this way, it looks like I actually get, by the definition of ET, I do actually get a pretty defined answer, which is this way. So if ET is this way, so forget about this one here. And I do know that EN must point in the, basically the inside of the parabola. What is EB? Big EZ, right? Okay. So does that spare me from doing that craziness? Probably. Because I have two of the vectors, I just do the cross product to find the n, right? That's great. So instead of jumping into calculations, I think that stopping and looking at the problem a little longer can actually get you to shortcuts. That are not just shortcuts, it's just a smarter way of doing things. So I did apply, at some point you have to apply some definitions. I did apply the definition of ET, and I actually do it with these coordinate systems, and I find something that actually is telling me which way ET is pointing. EN, I do know, again, go back to your book, that it's actually going that way. So now I just have to compute it. So EB is easy. Okay, fine. So what is EN? I have ET and EB. How do I write EN? Don't give me the solution. It's just the cross product in which order?
It's EB cross ET.
Okay. So this is big EZ crossed with that ugly expression there, plus x over b EY over 1 plus x dot squared b squared. Okay. And then where do you want this? Probably go up there. What do I get? What is EZ crossed with EX? EY? Is it EY? Then EZ crossed with EY? Does it make sense? This is EN. This is a vector that is supposed to be in the same plane of ET, perpendicular to ET. Does it look familiar? You've probably seen this before. You have a vector given by its two components. You swap them and change the sign of one of them, and you get the perpendicular vector. That's what I see here. I'm swapping the components. X over b was multiplying EY. Now it's gone to EX, and it's changed the sign, and the 1 has been swapped between EX and EY. If you do the dot product between the two, you get 0. These are all sanity checks. Now, okay, so say that you have to do this. This will be the way. It will be one way, but am I leaving something out here? Do you think this was all correct? I'm not saying it's not. I'm just questioning it. Before I move on, I always question what I do, because if I don't usually...
That thing's not rotating.
I'm assuming that, again, no, it can rotate. I can choose the way these vectors are defined. Remember, they are defined in certain reference frames. So I picked G. So this is G. This is G. But if this was rotating, then I can call the reference frame of the parabola A, and I can use A, right?
Yeah, but your velocity will be different, so your ET will be...
No, if I see it with the parabola, it's the same. It's the same thing.
Okay.
Well, you can change the names of these coordinate axes. It will be a little ex, maybe big, little ey, little ez. But
Oh, you're saying...
so I see it with the parabola. I just see the same kind of motion. So forget about rotating, not rotating here. And I suggest you do that. You do go with the line that is moving to compute these intrinsic coordinates. Go back to your notes. We defined intrinsic coordinates. They depend on the trajectory. The trajectory depends on the reference frame in which you're sitting. So you pick that. You can pick the one of the parabola, for example. That makes your life easier. So this point that I was making before, that this could have gone the other way, it doesn't matter anymore.
The condition for the sign of the quadrant.
We sure? I think that should actually go down. There was something here that I did, and I erased it. What was before I simplified here? What did I have? I had x dot, ex. I'm talking about et. This is et, right? I think this looked like these.
Yeah.
And then I had...
So what you factor out as the next set is actually the absolute value of x.
Right. That's what happened.
Yeah.
I can bring these out, but if it's positive, I get these. If it's negative, I don't get these. There's a minus in front of it, right?
The minus in front of it, yeah.
So careful with this stuff. Because I do know, by looking at the problem, that every problem we're addressing will have some initial conditions. When you get to differential equations, someone has to give you an initial position and an initial velocity, because we get second order differential equations. So in order for you to solve them, you need two initial conditions. So if the differential equation you get, as in this case, would be x double dot, to solve it, you will need x at time 0, or at a given time, and an x dot at that time. So it depends on the sign of the velocity, of course, because you may be here, and you may be going that way, or this other way. So that needs to matter to give you the direction of that. So that's why I would never give you a problem with the parabola rotating, probably. Because because you have to start going through all the subcases. You have the case where the x dot is positive and you get these. You have the case where x dot is negative and you get these with the minus in front. So the en remains the same, but the eb is going to be different. Right? So you may get a lot of problems where you have multiple cases, and you can't ignore them.
Just put a dummy variable and then call it a and say equal to 1 if x dot is greater than 0 or
Yeah.
negative 1 if
But the point is, you can't.
I would just leave it like in the original form and try to use that.
Yes, true. You can do that as well. Yeah. So my point is, stop and think and look at the problem as you do your calculations, because they may not actually be capturing everything that is going on if you don't think hard enough. So when I see these, I know that it is possible that the velocity goes in two different directions. It is possible. Why not? Depends on the initial conditions. It depends on if that particle is moving with a certain velocity at initial time. It can go up and then come down. But anyways, we're not doing this, but I think this is a good exercise. Do we all agree on this at this point? But say that I don't need all this stuff. Let's try to apply, which form do you want to apply? Because I don't think I can do both of them. I want to apply the alternate form. That's probably a good idea. Why? Because we have observed that in this case, the reaction, nothing is spinning here. The reaction is only along the en direction, so the velocity is obviously along the, doesn't matter which way it's going. The velocity with respect to the ground is perpendicular, so the r dotted with vg, which is basically going to be my non-conservative force dotted with vg, is 0. So I can use d Tn plus u dt equals to 0. The total energy is conserved in this problem. So let's do that. Okay, T is, I need to find T and U. T in N, did you write this last time? 1 over 2 m v g dotted with vg. Remember, g is inertial, is 1 over 2 that ugly expression squared. What is it? X dot squared plus x dot everything squared over b. That's it? Can you check? B squared? Yeah, thank you. Let me just factor out x dot squared just for fun. 1 plus x over b squared. Doesn't really look much nicer, but we got that already, yeah? Is that right?
It's like 1/2 m times 2x dot plus 2x times x dot cubed divided by b squared plus 2x squared times.
Are you talking about the derivative already?
Yeah.
Okay, I'm not doing that yet. Yeah, I'm sorry, I'm not doing that. I'm redoing this. I can't, yeah, I need to. Okay, I told you to go and study in your book all the different potential functions that belong to constant force like gravity, spring forces, etc. Go and do it. You can study the derivation or not. You just need to know that they exist. Okay, so let's do this. What is this? Minus, okay, EY is actually pointing the opposite direction, so mg is actually minus, this is a minus GEY, right? And this is dotted with R, and R is XEX plus Y, well, I know that Y is that expression there, x squared over 2b EY. Correct? Okay, these minuses go away here. EY dotted with the x is 0. All I'm left with is this EY here. And so I have mg x squared over 2b. That's it? Yep. Okay. So my total energy is Tn plus u. This is a scalar already, of course. I have to sum them up. X dot squared multiplies 1 plus x over b squared. That's it. Plus mg x squared over 2b. And now I have to take the derivative of this. Okay. dE and dt. This is going to be fun. Okay. 1 over 2 mass. Then I have a 2 x dot x double dot. Let's actually open a parenthesis here. So I'm taking the derivative of this times this times 1 plus x over b, both squared. And then I have x dot squared that multiplies. What do I get? Get this. That's the first. And then the last one is, they're all constants there. I see a mg, let's simplify quickly here, mg over b x dot equals 0. And that's the end. I mean, you can manipulate these as much as you want. That's your differential equation of motion already. Pretty ugly, huh? They don't need to be nice all the time. So if I had done this the other way, well, d dt of Tn is this term that I've just computed here, right? So I already had, I would have this already. I will have to compute this guy here. Okay, let's just do it. We have a few more minutes. Well, F is mg plus this reaction. And we said that this is minus mg big EY plus some r we don't know, En, right? Yep. I have to dot this with V. How would you do that? Okay, the first one is minus mg big EY that is dotted with the velocity vector, which is, we said, x dot Ex plus, I don't know what this was. This was some x dot x over 2 Ey. I forgot already. Is this right? Oh, B. Is this right? I think so, right? Yeah. And this is easy. I mean, the first one goes away. Second one gives me this. Makes sense. It must give me that. They have to give me the same equation, right? So the second term is Ren dotted with V. Well, I'm sorry, this is ground. I mean, we said that the ground is inertia, right? So V ground, I mean, I know that these two are perpendicular, so I'm going to say that this is 0, but another way to say so is that this can also be expressed as Ren dotted with the norm of Vg Et, right? You can write the velocity that way. So this is 0. Does it give me the same equation? Let's focus on this term here. It should. Of this dot product, all I have left is, so from all these ugliness, what I get is, what do I get? Minus mg x dot x over b. And that's exactly what I see there, except this is going to be your right-hand side of this equation. You bring it to the left-hand side, you get the same exact equation. That's nothing special. So, as I said, work energy is it's not particularly exciting. Is a way to solve specific problems where you may have constraints, like in this case, and it may make your calculation more algebraic than vectorial, pretty much. That's really what is happening. It does become very interesting and useful when we'll study Lagrange's equations, because Lagrange's equations, as I told you, they do deal with constraints in a pretty nice way. And so now, at that point, energy becomes really an important element for writing equations of motion that way. So this really concludes chapter 3 from my point of view. This is all you should expect in chapter 3. I hope you agree with me that there's very little to memorize here. There's really very little that you need to memorize, especially because you can use your book notes, whatever you want. Think about the problems. Stare at them for a while before you start writing anything. That's really my advice. I decided the problems will be 4 problems. What problems? Questions. Some are problems, some are really questions, just to test your understanding. So don't jump into calculating stuff before you think. Again, they're not all problems. Some are really just testing your understanding. Yeah, you may need to write down some vectors, some calculations, but they're not really complete problems in some cases. And they're all weighted. It's 100 points. I think some will be 20, 125, or something like that. They will be pretty similar in terms of the time that you should invest on them. Maybe there is one that is a little longer, like 30 points. There are office hours today. There are office hours on Monday, not the day of the test. Email me for anything. I'm always available. I'll be on travel Thursday and Friday, but I should be able to respond to questions. We all feel confident with kinematics and kinetics? You sure? Okay, next is systems of particles, and we'll do it in the next room, if you're available.